Good morning. Before we go to metrology and chemistry, actual metrology and chemistry, there are two things we need to discuss. Yeah? The first one concerns only each students, and this is about this afternoon seminar. And I simply want to reiterate today there will be Koit Herodes doing the LCMS remote lab with you. I maybe also come just to see how it goes and learn a little bit. But otherwise, yeah, it is today a completely different thing from what it has been in the previous weeks. And now the second question concerns all of you who take this metrology and chemistry course. We now have essentially finished uncertainty part of this course, and we are now ready to take test number 1. Yeah, you may remember from the course introduction, there will be two interim tests, each giving 10% of the overall grade. I do not want to use lecture time for that test. We are already slightly lagging behind with time because we lost some lectures. Therefore, I'd like to use any time that is suitable for you. It can be evening, it can be Saturday, because everything is on Moodle. Yeah, I don't need to be here. You don't need to be here. You can take it from wherever you wish. Now, we will define some time frame, let's say 4 hours, within which you can do the test. We typically have given 1.5 hours, meaning 1 hour, 30 minutes for the test, but actually people typically do it far less with 1 hour. So actually this time is massively over, just not to force you to be in a hurry. This test is not so difficult, but it is really important that you very carefully read the question. Do not hurry. Yeah? So 4 hours. And within that 4 hours, when you start doing the test, you will have 1 hour and 30 minutes. And now, question to you: when will we do that? If we can decide today, excellent. If not, we decide next week. As I said, any 4-hour time slot from any day is suitable because it's in Moodle. It's fully up to you. Say you again. No, it will be 1 day. Yeah. Okay. I can also explain why only 4 hours and why only 1 day. Technically, it's extremely easy to keep the test open for you for 1 week, for example. So everybody can choose which time. But yeah, as you probably guess, there might be a big temptation to go to your colleagues and ask who have already done the test and ask what questions there will be and so on and so forth. So we want to minimize the probability of any fraud. Yeah. So it is not allowed that you do the test and then you go and start teaching others. And if the time is very long, like 1 week or several days, then this temptation might become very big. So this is why we keep it relatively short. But 4 hours is quite okay. Yeah, it can be from 6 to 10 then, or maybe from 5 to 9, whichever you. And Hamdi, you said next Thursday or next Friday. Was that your proposal? Meaning not this week, but next week? Monday afternoon. Okay, let's do so. We are not desperate with time. Actually, we don't need to do it immediately. It's pretty much up to you, yeah, when you want. Please discuss among you. And next Tuesday, please remind me that we will come back to this question. Perhaps even what we could do, yeah. I would be very happy if you would take lead, yeah. So because otherwise I will simply forget. There is a forum here called Questions and Answers, yeah, in Moodle. You can also post there. So any of you, please take lead and post there some kind of polling or whatever. So initiate discussion, because also not everybody is here right now, yeah. Especially I see only one Estonian student. who will then otherwise be left out of the loop. Yeah, it's actually, in a way, it would not be polite to make the decision today, because then they are completely out of discussion. So please start discussion there, maybe make some doodle or whatever thing you wish to do. And we return to this discussion next week. Is this suitable? Yeah. Okay, but please don't forget, yeah, because otherwise what can happen, for me, it is perfectly okay to do this test also at the end of May. But at the end of May, you have tons of exams and presentations and group works and all kinds of things. Yeah, so the sooner we get it out of hand, yeah, the better it is. Also, let me say that let me say that this test has one peculiarity. You cannot fail it. Meaning, if you get 0, it's still considered pass. You simply lose points from your final exam grade. But since you cannot fail, you also cannot retake. There's no such thing as retaking that test. And also, taking that test is not mandatory. You are welcome to completely ignore this old test question, but then automatically you have 10% points lost, so you lose 1 grade. Yeah, if your exam answer is like good for an A, you get B, and so on. This is also why I'm stressing read very carefully, because you have only 1 attempt. Okay, but then we have now finished these organizational discussions. So let us now go to this calculation. Did you try at home? Did you manage to finish? Who has managed to finish it and get as far as this is here? Okay, almost everybody except 1 or 2 people. Yeah, okay, yeah, thank you. Yeah. Anybody has any questions? Is there anything I need to still to help or explain to anybody why something was done as it was done? Okay, yeah. Nobody is asking anything. But then let us spend a little more time here. Now, please look at these indices. Is there anything interesting that you notice? Okay. What might be the reason? Why does it have so big weight? Huh? What might be the reason? Indeed. Calibration graph contributes less than 25% of the uncertainty, and more than 3/4 come from the measurement of the sample. Interesting, huh? Gleb seems to have an idea. Yeah? There should be some microphone somewhere, not too far. Yeah.
It's just that as you began questioning such things, I suddenly began having questions about this work all of a sudden. But
yeah, please ask. Yeah. This is why we are here.
I can't quite explain why the sample has such high uncertainty, because its uncertainty that arises from the data is precisely the same as the uncertainty of the A3, does not have such index whatsoever. So
yeah. Now let's look at the uncertainties. You see that in the calibration graph samples, the uncertainties actually are, in broad terms, proportional to signals, and this is very often the case in instrumental analysis. The bigger signals, also like bigger, let's say, I don't mean noise, or I don't mean baseline noise, but let's say bigger repeatability, standard deviation of integrating, and bigger things like that, and they often tend to be proportional. But now, if you look at this signal, it's not in the same proportion. It is approximately the same signal intensity as solution number 2, which has uncertainty 0.02, but this one has 0.03. What do you think? Is this by accident or not? Hamdi, Gleb, can you pass the microphone?
I think mainly the reason from the equation. So if we look at B0 or like B1, which C's and A's contribute to, they are either like subtracted or divided. So when we have like an increase due to uncertainty, the components it will not be as contributing much as A sample. Because when we do uncertainty to A sample, we add like the delta. So when we add the delta to A sample, which is give higher component, or but with B0 or B1, the addition will be less.
This can be. Let me come back to this, but let me for a moment concentrate on why is this uncertainty here relatively bigger than these uncertainties. Have I simply made a typo? Have I just put some number, without thinking, or do I have some? Please, give them,
I'm not sure. Maybe the slope and the intercept. In the intercept, only have like the uncertainty is mainly due to the standard deviation that you may obtain from the graph, but the sample may include the uncertainty due to repeatability, drift, or like other uncertainty sources, not only from the graph that you may.
I think you are on the right track, but the examples that you gave were not really good ones. I will explain what I mean.
I think for calibration, we can decide the max split component, and for the sample, we have possible interferences.
Wow, this is already, okay. So you essentially, I think, got it. Let's see. These absorbances or signals, whatever they are measured from calibration solutions, which typically don't have any interfering compounds. There's no any extraction or no such difficulties involved. But this one is measured from the sample solution. Here there can be additional peaks, partial peak overlap, etc. So oftentimes the signal measured for the sample solution has much bigger uncertainty than calibration graph signals, simply because calibration graphs are measured from, are typically, not always, typically from artificial samples. That you simply prepare nice, clean solutions, just analyze them. But in this solution, which you have obtained from sample preparation, there can be all kinds of nasty things in addition. So that, Maitane, I think you said the right thing, but had you said like interferences possible, I don't know, analyze, let's put it, extraction problems, etc., which might all be accounted for in this A sample, then this would have been a perfect answer. All right, now, good. This justifies somewhat larger uncertainty, and I can tell you that actually all those interference, etc., things can actually even lead to much bigger uncertainty. So that the 0.03 is rather like quite modest. I think in many real situations, it might easily be 0.05 or something like that. Again, we assume rectangular distribution. And if you see what has happened now, then you see that calibration graph gives 10% of all the uncertainty. So this is one thing. This is one reason, but it's not all. Let's suppose now we put here also 0.02. This will make this uncertainty pretty much the same as this one here. So now it would be very reasonable to expect, okay, now all the signals should sort of contribute more or less equal, Gleb is laughing. You probably tried already, this is what I thought. All right, that's what we see. Nothing of that kind. And now, Hamdi, I'm now coming to your answer, You said that this is because of this like model kind of thing, but it is in many ways, but you see, it's not as simple as just that, okay, this is here in the numerator, here we subtract, because actually any uncertainty in A sample and any uncertainty in B0 will have exactly the same contribution or exactly the same effect on C sample. So you see, if the same amount of uncertainty is in A sample or the same amount of uncertainty is in B0, it will contribute the same way to C sample uncertainty. Apparently, this is not the case. Balong?
I think that for slope and intercept calculation, we mostly use the mean of concentration and the signal, so the effect will be 3 times lower than for A sample uncertainty.
Please say it again. I think you said the right thing. Could you repeat so that I can clearly hear what you said?
For slope, like for B1 and B0 calculation, we use mostly the mean of concentration and the absorbance to calculate the slope and intercept. So assume that the uncertainty is the same for everything, so that the effect will be 3 times lower than uncertainty of the sample, because we have 3 concentration and 3 signals, so the mean will be divided by 3.
This is very well said. Usually in this course, when I ask this thing, usually people don't come up with this answer. So this is very nice. Usually people don't guess it. So what Balong explained, and very correctly, is any calibration graph from many points, by its very nature, is an averaging operation. So the different points, they all make it in a kind of an averaged way, this calibration graph. So Balong said that it will be 3 times smaller, but actually it will be like square root of 3 times. Because when you do average, you don't divide by how many you had, but you divide by square root of how many. So we can try to see what happens if, let's put it here, 0.01. Let's see what now. And now you see it's still dominating, by the way. But now it's already sort of comparable, to what it was. But there's one more thing that is also very important. And Hamdi, now again I come to your answer. It was a very good answer. Let me let me put this here like this. Yeah. In any calibration graph, slope and intercept are always negatively correlated. What that means? If into any, if into any of these data, if I take any of these data points and I little bit modify, no matter if I increase or decrease, most of the time what happens is that slope and, of course, slope and intercept, of course, both change. But if one increases, the other decreases. Or the other increases, the first one decreases. We can demonstrate that if you wish. And this is a well-known phenomenon. They are correlated to quite a high extent. It of course depends how many points and so on. So there are more things in that. It also depends how big the intercept is. This is also an important thing. But now, if you see, if slope gets bigger, let's now examine this equation. If slope gets bigger, this will be smaller. But if intercept at the same time will become smaller, then the numerator will be reduced less, so that any change in slope will be compensated by the change in the intercept. Yeah, when intercept becomes bigger, yeah, this is like reduced more, but then slope becomes smaller, so that by the denominator again now the quantity is not reduced so much. So this mutual compensation is one more thing which determines quite a bit. And also it is actually very important where on this calibration graph is your sample. I did not explain that, but if you now look, it is perfectly in the middle. So let's say close to perfectly. Yeah? The middle calibration sample of 0.55 is 0.49. Yeah? So you can't have a better match between sample and calibration graph than what you picture here. And there, the compensation between slope and intercept works like especially well. Let's see what happens if we move it closer to the limit. Yeah, let's put it something like 79. Yeah? See what happened. Not at all as dominating anymore. And by the way, the relative uncertainty now is smaller than it was previously. No? Let's make it now 0.27. Yeah? Still quite dominant, but now it is dominant, of course, because now its uncertainty is huge. If we now, I mean, with respect to the quantity itself. If we now write here 0.02, again we see that it's not as dominating now. Okay, now now I've explained so many things, and you might be over. What did he want to tell us? Yeah. So I would like to give like take-home messages that first of all, calibration graph uncertainty and contribution to uncertainty from different points of calibration graph, it's a very tricky thing, not so straightforward. Secondly, calibration graph is a big averaging machine, yeah, in a way. This also is the reason why people typically don't do calibration graphs from, let's say, 25 points. I would say usually it's not more than 10 points, and very often it's something like 7, maybe 8, maybe even 6, and so, because there's not so much reason to do many more points, because in any way it will be mainly the sample measurement that is responsible for all this. But now, the last thing, which is also very important as take-home message, is this whole thing that I'm now explaining works very nice indeed if your sample signal is in the middle of the calibration graph. But what happens quite often in real life is people make calibration graphs with some, let's say, middle range concentrations. But then in most of the samples, the concentrations are very low. So everything is at the low end of the calibration. And then the uncertainty from the calibration graph can be much bigger. There can be mismatches between calibration graph and the points. And there are actually some, let's say, quite dangerous situations possible where you can go completely wrong, even though from the distance your calibration graph looks very good. I will come back to these things in validation part when we will discuss, among other things, linearity, and then I will try to explain what I mean here. So let's just say that in the case of usual chemical analysis, if your sample signal is somewhere more or less in the mid-range of the calibration graph, and calibration graph is more or less nicely linear, then usually calibration graph is not a big contributor to uncertainty. It is a contributor, certainly it needs to be taken into account. Yes, here also you see let's say 23%. Yeah, it's significant. Yeah, but of course it is dispersed between these numerous input quantities. But in any case, measurement of the sample solution tends to be much more consequential, much more. Ola, yeah. Would you pass the microphone? There's also the cubic up there. You can also use that. Yeah.
Just like a quick question, because Ivo, you said that the slope and intercept are correlated, right? So then shouldn't we account for that in our uncertainty calculation? Because at the beginning of the semester, you mentioned that you should, if your inputs are highly correlated.
So good that you asked it. I forgot to mention that. We absolutely should, and we are. If you calculate like this, then it is accounted for. But if we would treat slope and intercept as two input quantities and then would not calculate any correlation between, then we would not. This is, if you go to the online course, in online course section 9, in the online course ISOGAM section, there's a huge application example of ammonia determination in spectrophotometry, and there we neglect that correlation. I had a lot of thinking, how should I do? I did not want to neglect it, but I did not want to make the course too difficult. That section is already by far the most difficult for all the participants. So I decided to simply neglect correlation, and there's a footnote which explains those things. It gives a link to somewhere where you can get the full story. It also says how much uncertainty will be overestimated. You know? It's not so much, there's nothing tragic. And also why I supports neglecting correlation in the online course is that if you neglect correlation between slope and intercept, you always get somewhat higher uncertainty, not lower. I don't want to start explaining now why always higher. It can be shown mathematically, but let's not go into it. So it's not such a big tragedy. But yeah, beautiful question. Yeah, very, very. Now somebody else had hand up, which Gleb, yeah. Okay.
Could you explain once more? I did not understand how we are accounting for the correlation right here.
We are accounting for correlation by not having B1 and B0 as input quantities. They are interim quantities. Input quantities are all these. True, if, for example, if you make concentrations from the same stock solution, they also are correlated. So some small correlation might still remain. But the big correlation that comes from the statistics from this slope versus intercept, that will be removed. So interim quantities in models oftentimes can be correlated. But if you go back to the initial, like fundamental quantities that cause them, then this correlation is automatically accounted for.
Thank you for answer. My second question was about the usage of relative uncertainties in Krachten approach. Can we do that at all? Because right here we are adding the quantities, not like multiplying or something.
Yeah, here we cannot. And this is not about Krachten approach. This is about the ISO-GAM modeling altogether. In all cases, when you work in model-based way, you have those quantities, they have concrete values that you are putting in. So see, I'm not calculating some generalized uncertainty, and then I'm not assigning it to my result. Instead, I put in my value that I got from my chromatogram or spectrophotometer today. I'm putting in real values that I had today. So I put in also the real uncertainties in the same units. So no, we don't really do that. In some sophisticated cases, there might be some interim calculations via some relative, but no, the way this Krachten matrix works obviously is that this number has to be additive to this. Otherwise, you are not allowed to add, yeah, if they're not saying the same unit. So every uncertainty contribution comes with its own units. Claire, did I answer?
Yes, thank you.
Okay, let me now show one more thing. I remember some of you said that you haven't learned the intercept function, or so to LINEST function that you haven't really used. I want to show you this function. It's a very useful thing. Yeah. So let's do. I put it here. Now, LINEST is a strange kind of function. It's a matrix function, meaning it does not return a value. Yeah, almost all those functions that we are using return a value, but LINEST returns a matrix. It gives a set of values. And now there's an interesting thing. The way LINEST is entered differs between versions of Excel. And I guess many of you might have now, as we've already seen in one other instance, we saw that some version difference made a difference between me and Hans. I guess now also this can happen. So I will first show you how I do in my Excel. That should probably work in your Excels also. And then I can say what probably is the different thing in your Excel. So now I'm inserting it is in my Excel at least. It's slightly tricky. So just do as I say. Don't hurry. Yeah? Follow me. Yeah. So start typing like this. LINEST. And now you put parentheses. And now we need y's, the y-axis. Yeah. Y's in our case are these a's. Yeah. So we take this. Oh. Now we need x's. X's are concentrations. So we take this. Yeah. Again, I'm putting semicolons, but you might be putting commas. Yeah, depending on what you. And now we have two more parameters that we need to insert. Here now the third parameter is either 1 or 0. 1 is in usual linear regression. 0 is if you want to force intercept to 0. So in this case we put 1. And the last parameter tells us if we want additional regression statistics. And yes, we want. This is actually the whole idea why I'm teaching this function to you. It's very useful. So we put here also 1. And now we close the parentheses. And now, in my Excel, in order to get this whole thing correct, I need to press Control-Shift-Enter. Yeah? But I think in your Excel, you might be able to just press it. See? I made a big mistake. Oh, very sorry. I made a mistake in forgetting one important thing. I first need to select an area where this matrix will be put. Oh, very sorry. Let's start again. The area should be 2 columns and 3 rows. It can also be 5 rows, but down there's some statistics which not so very useful. And now you start inserting it just the same way, and now you press either Control-Shift-Enter or simply Enter, depending on which Excel. And now you should see something like this. Let me save. So now it already is in the Moodle system. Did you manage? I'm so sorry for my clumsy and not so good explanation. Is anybody in trouble not getting this kind of thing? Did you press Enter or Control-Shift-Enter? And it worked like this. Okay, you might also press just Enter. Did anybody get numbers also here? Even though you marked only 3 rows, you got 5 rows. I think this new Excel does this kind of thing, that even if you mark a smaller area, you still get the big one. Okay, good. In any case, if you manage to get these numbers, then very nice. Now, what do they mean? Let me first explain what this matrix means. These, in my case now 6, in your case maybe 10 different values. These are all one set. You cannot remove them or edit or do anything separate. For example, suppose I want to delete this one. It tells me, you now don't see. Try to delete one of those, and it will tell you, you cannot change part of an array. You can only delete them all together. You cannot delete them separately. Also, if you edit them, you can edit any of these. If you go and press edit, you can edit any of these. This automatically means editing all of them. Yeah? Now what they mean. This is slope. This is standard deviation of the slope. And this is R squared. This is the intercept. This is standard deviation of the intercept. And this is the standard deviation of the regression, meaning root mean square average of the deviations of the data points around calibration. This is also pretty useful. R squared, you of course know well what it is. And these are also sometimes very useful, the standard deviations of the regression parameters. So, let me save. And now I can give you easily the demonstration that slope and intercept are correlated. So let's see. Let's write here, instead of 0.26, let's write here 0.25. Let us copy these as values here so that we know what they must be. And now we will look at what will happen. Yeah? Let's put here now 0.27. Yeah? Okay, what happened? Slope became smaller. Yeah, it's smaller. Intercept became bigger. Okay, let's see. Let's maybe change this one. Yeah, 0.033. Let's put 0.034. Okay. Slope again became smaller. Intercept again became bigger. Yeah. By bigger, I mean more positive. Yeah. If intercept is initially negative, then it goes more. Okay. But now let's make this one bigger. Yeah, 0.011. Let's put 0.0. Or yeah, okay. Yeah, let's put 0.01. Okay, now slope became smaller, intercept again bigger, but if we put here 0.012, now slope became bigger, intercept became smaller, and I think you may find somewhere some possibility to change something so that both can become bigger or small, but you have to really carefully try it out. if you just randomly change in almost every case, you get it like I'm showing. So let's see. Let's make this 0.5. Let's put here simply 0.5. Okay. This became smaller. Aha, and this also. So now I got one situation when both of them became smaller. But see how many times I had to try all kinds of different things. Yeah? So this apparently is the last thing I wish to explain here. Any questions, anybody? I think we now have played with this file enough and can stop. Now you will be able to solve homework linear regression. Now there's a homework. And then there's a homework complex analysis, which also involves that. But complex analysis also involves recovery uncertainty and spiking, which is tricky. We will learn that as we go with reference materials. So you might perhaps still not be able to do the complex analysis. Although one of you, as I think I said already some time ago, one of you did all the homeworks already, and long time ago. That has never happened. Really, I was really surprised to see that. All tens. Never happened before. Okay, any questions here? Please raise, oh yeah, I haven't almost asked at all. Please raise your hand who think that more or less understood what I was trying to explain. Elvin, Carlo. Aha, okay. Yeah, good. Everybody understood. Then, what we will do, I will now take back control here. And as promised, we now start a completely new section, the second section of this course, which has reference materials and interlaboratory comparisons. So we now have learned all the basics, all the basic concepts, etc., measurements and results, and all those repeatabilities and all those things. And now we go to two extremely practical and useful tools that exist in metrology and chemistry, which are reference materials and interlaboratory comparisons. And today we start with reference materials. It can happen that already next time we do some calculation of recovery with spiking. I cannot promise that we reach there next time, but we may, so that if possible, bring your PC so that you have it. So the tool reference materials are really, if you look here, tools for all these things, and these are all pretty important things, so you hopefully will find them. Let us start first with classifications, definitions, and all those kinds of things. So first of all, we can classify and define CRMs by their status. And firstly, simply reference material, what that means. This is now the Vim definition, yeah. Material sufficiently homogeneous, it's homogeneous, and stable, so homogeneity, stability, with reference to specified properties which has been established to be fit for its intended purpose in measurement or in examination nominal properties. Now, we have here in this course already discussed something that very well matches this. What was it? Has come up several times during the course already. Something. Could you throw the cubic? Yeah.
That control samples?
Exactly. Control chart, control sample is a typical reference material the way it is written here. I think I explained that it has to be homogeneous, yeah, because you take all the subsamples, they must be as identical as possible, and it has to be stable for some time, yeah. So indeed, those samples with which you, for example, determine within lab reproducibility, typical, yeah, reference. Okay. And if you notice, this definition does not include that you have to know very accurately what is the value of this concentration there. That is not mentioned at all. And like I said, in control sample, we don't need to have any reference value. That value will simply like be generated by our own long-term measurements, yeah. But it does not need to be any like high-level metrological anything. So here are some possible reference materials. Yeah. And yeah, it can be anything, just let's say some protein reference material in milk powder, but it can also be like steel with some elements, it can be main components, it can be water with trace elements, etc. So numerous, like infinite number of examples can be given what it can. And reference materials, as you see, can be prepared in any laboratory, and these are then called laboratory reference materials. And again, these control samples for control charts are typical laboratory reference materials. You see, I'll come to that. Any certified reference material at the same time is also a reference material. Yeah, it can be a certified reference material. But even if it is a certified reference material, it still falls under this definition. You see, any certified reference material is also a reference material by definition. Simply, there are more requirements, which I'll come to. Yeah. Okay. Also, perhaps, which I did not mention, all calibration graph solutions can also be considered reference materials. And calibration graph solutions that you prepare in your lab are typical laboratory reference materials. Okay. And now I'm coming to Hamdi's comment. Yeah. Now, a subsection of reference materials is certified reference. Certified reference material is a reference material, so it falls under the definition of the reference material. But in addition to just being reference material, it is accompanied by documentation issued by an authoritative body, is some producer of certified reference material, providing one or more specified property values. So the property values in our chemistry, of course, oftentimes are analyte concentrations. You know? Not always, but most of the time. And here now we have the requirement that these values have also uncertainties and traceability, which in reference material we did not have. So this reference material typically also has some value. Yeah, I mean, even if you use it as control chart sample, it eventually will have some average value from all your measurements over the time. But it does not need to have traceability or uncertainty. So we can say that certified reference material is a kind of higher level or higher order reference material. Christian says, I think new definition now explicitly says metrological. Yeah, I think you might be right. Yes, yeah, absolutely. Thank you for saying. I'll make a note for myself so that I will recheck. Now, the next thing, we can classify by composition. First of all, it can be pure substances. So, for example, if you buy some standard substance for making a calibration graph, this is in the reference material. You can buy solutions, or you can make them in your lab. So again, calibration graph solutions that you made in your lab can be considered lab reference materials. But you can also buy certified solutions. So solution reference materials can also be certified reference materials. You buy and you get values and uncertainties and everything. For example, in many cases, people these days, if they do ICP-MS analysis of trace elements, maybe they want to determine 30 elements, then instead of buying 30 metals or 30 metal salts and then making solutions with weighing 30 times and so on, they rather oftentimes buy one solution where all those elements are in with concentrations and uncertainties, much easier and much simpler, much less work. And also, if you would, okay, it's not so cheap, yeah, but if you would buy all those metal salts separately, it'll also be expensive. Yeah, nobody gives them to you just for free. Yeah? So that quite often useful to do like this. So can be one analyte, several analytes. Sometimes also analyte and added interfering compound so that you can check your interferences. Then it can be artificial mixtures. Solutions are also artificial mixtures, but I make distinction here. So typical artificial mixtures are metal alloys, then different plastics, some, let's say, industrial concentrates which have different like components in them, etc. Artificial mixtures also, in principle, cement is an artificial mixture and glass is an artificial. They are all human-made, yeah. And now, to some extent, overlapping with this artificial mixture thing are matrix reference materials. These are now these reference materials that mimic real samples. These are now this milk powder which you can buy where there are trace elements inside, or you can buy drinking water with trace elements. You can buy soils of different kinds, plant leaves. You can buy all kinds of meat reference materials. Then you can buy sawdust. I mean, wood chip and then wood-based reference material, etc., etc., etc. So all kinds of materials, also sewage sludge, etc., yeah, where somebody has, with great care, determined the contents of the analytes. Matrix reference materials are often called MRMs, and if they are certified, then they are called as CMRM or MCRM. Yeah, can be this or can be that in the same. And LMRM are laboratory matrix reference materials. So in principle, in your control chart, you can use, as we discussed back then, you can use meat samples. So you make many meat samples and put them into freezer, and then every day you use that analysis method of meat. You take one of those and then use as control charts. Huh? Those meat samples then would be typical laboratory matrix reference. You prepared them yourself. They don't have certificate or any certified values, but you can use them for checking your. Before I continue, maybe there are questions. Apparently, no. Still.
I'm not sure whether it's like a general question or not. But if you prepare your control samples in your laboratory, how can you verify that? Because we are doing the same procedure, as you said, like you're going to make the same sample same day. For example, if you're talking about meat samples, you're going to take the control sample and you're going to do all the steps of sample preparation. How can you verify that we're not doing anything wrong? Because we are using we're doing the same steps even for sample and also for control samples. So maybe we are biased in some way, or maybe we are doing something wrong to both of them. Then how you can verify whether it's the right thing or not?
Very valid question. No? If we go back now to the part where I explained precision and also bias and trueness and all those things, then I explained that this control sample only shows precision or within lab reproducibility. Yes, we absolutely might be all the time doing something systematically wrong, so that we maybe lose half of our analyte, perfectly possible. But that sample does not tell us that, and is not supposed to. For that, we have those 4 approaches, yeah, which I mentioned for determining bias, which were analysis of certified reference materials, interlaboratory comparison, spiking study, yeah, reference, exactly. Those 4 are meant to find if you do something systematically. But control sample only tells you how well you do it the same way every day. Yeah, if the control sample results differ very much, you see, my results are not reproducible. Today it's much bigger, yesterday it was much smaller, and so on. So this is what control sample only can tell you. True, it is also possible, it's not usually done, but it is possible to use a certified reference material as control sample. And then you would be able every day to see both the random and the systematic effect. The trouble is that in order to run a control chart, you would need a lot of amount of the sample has to be big. But certified reference materials often are sold in maybe 10 grams or maybe 50, depending on situation. And maybe you will use it up in just 5, you analyze 5 times and it's all gone. Yeah, you don't have more. But if, for example, if you buy some CRM, let's say 100 milliliters, sometimes they are also 100 milliliters. And if every time you use for your analysis, maybe only 150 microliters, then my recommendation would be, yes, please use that CRM for your control sample. Then you have both of these things under control constantly. Did I answer? Okay. Yeah. All right. Now, here I have 3 items. So these are. Christian says, sorry, the definition of just in the draft of the new version, the Vim. Yeah, yes, okay. Christian, that's perfectly okay. In any case, this new Vim will be out at some point. So there's nothing wrong if already now we switch in our teaching materials. I made a note for the next year. So in any case, I will make that change before the lecture next year. And by next year, maybe the Vim 4 is already out. Yeah. Problem. Yeah. Now, these matrix reference materials can be obtained by 3 means, which is to some extent important. Natural means that, for example, let's say it's plant leaves. Yeah, natural means that, okay, you go out, there's some tree, yeah, and you collect those leaves. You bring the leaves back and you make the material. We will later see how reference materials are produced. I mean, how certified reference materials are produced. Laboratory reference materials, similarly, yeah, in the case of plant leaves, it always involves some homogenization, etc. So naturally, you just take what is out there. Now, fortified means that you wish to have higher analyte content. So let's see, for example, you want to have lead in plant leaves. You see, in most places, at least in this country, the concentration of lead in soil is so low that plant leaves don't contain almost any lead at all. And also now gasoline, leaded gasoline, long ago is not used in this country, and I guess probably in most of your countries also. So also at roadside, you don't get more lead, or at least not much more lead into plant leaves. So what do? You pick some tree or some plant and you pour water on that plant where you put some lead salt in. So that when the plant takes salts and water, into its leaves and etc., then lead is there. And then, so you essentially, sad to say, you sort of poison the plant. The plant usually doesn't really suffer much. So as long as you don't put too much, it's probably okay. But now, if you take those plant leaves, they will be much higher, having much higher lead content than they would otherwise have. This is fortified. And now spiked means you go out, again, you find the plant, these are probably very okay leaves, you take those leaves, the lead is very low there, but now you mix, and now you add some lead salt, and then you again mix very well. So you take the material the way it is, and then add more analyte so that the analyte content will be higher. So these are the three main ways. Now, question to you, between these two, which of these would you prefer? Which of these is supposed to give more accurate, more relevant reference? Either spiked or fortified. So if you want higher analyte content, should it be spiked or fortified? Or does it matter, or it's just all the same? Lead.
I can only give the example you gave yourself with the soil, where we try to infuse the soil with the lead or some other compounds we want, but it doesn't go quite in the places you want to go. And in case of fortification, we exactly manage to put the analyte in the place we want it to be. So fortification is better in any way.
Correct. Yeah. Sad we don't have exam today. Would be very, very good exam points. So if I take green color for a moment, and then try to draw a plant leaf, then plant leaf looks something like this. And it has these things which I don't know how to call in English, but I think you understand what these are. So this is a typical plant leaf. And now, this matter here is pretty soft, but this is quite hard, and this is especially hard, and then oftentimes like very cellulosic, If you now mix this thing well, then of course this part will be like beaten into small pieces, but this will not. And now any added lead most likely will not go into these parts nearly as well as it will go into these parts. And any added lead will not go so well between the fibers of the cellulose inside cell walls and so on and so forth. So indeed, in this, in the case of solid, in the case of solid materials, especially if they are inhomogeneous solid materials, spiking is not really an option to make reference materials with higher concentrations, because the analyte that you add will most likely be much better extractable from that material afterwards than the analyte that originally was there. So incurring or fortification then would be much, much preferred. Although that is also, of course, more difficult and more costly to make. Yeah, you need to have that plant and you have to pour water, and I mean, you cannot do that really outside in any place because you are not supposed to poison the soil. So you probably have to have some special place where you grow them, and so on and so forth. Yeah, so this needs more organization. Okay. Yeah, Andy. Could you take the?
I will. I understand. If we speak like on another, so spiking, we add like sodium to then is like feeds animal itself.
Yes, exactly.
So after we feed it with right after long term, we'll accumulate
Yes.
sodium or other chemical, and then
Sodium perhaps not such a big issue. Yeah, but let's say veterinary drugs. Yeah, this is something that is quite important. Yeah, yes. Then you have to have a special animal whom you give much more veterinary drugs than is allowed. Yeah, and when you slaughter that animal, the meat will contain more.
so after a while.
Yeah, it will be, I would not say better, it simply reflects better the real life, yeah. More adequate, yeah, for the analysis. I think they do, yes. With animals, it's of course it's even more tricky, yeah. Okay, you cannot bring a cow into your lab, so you probably have to make a contract with somebody, some big farm, yeah, okay, there are many animals there. Okay, this animal, yeah, we will pay you money and you keep this animal completely separate, yeah, and then when it's slaughtered, it's like also handled separately, and all the meat will be then shipped to us. If, of course, costs a lot of money because the farmer then needs to all the time account for this one animal in a separate way, yeah. Okay. Anything else? Anybody? Gleb?
So I was wondering, how do you determine the analyte content in fortified materials? Because in case of spiking, you know really well how much you put the analyte in. In case of fortifying, you don't know anything about it. So in the end, you should like use also other methods and inter-laboratory comparisons, because you cannot use certified reference materials. You are making certified reference materials. What do you do in that case?
If you think about it, if you make these natural reference materials so that you simply go out and take tree leaves, then here you also don't know initially anything how much is inside. And obviously those tree leaves are collected and are mixed well and so on and so forth, and then analysis is performed. So expert labs typically determine the reference values. And even if you spike, it's still usually necessary that an expert lab still analyzes, because there might have been some amount of analyte in there already previously. So that except in few cases, such as these solutions and maybe a few more, most reference materials cannot be prepared by formulation. We will later see there are like two big ways how you can prepare certified reference material, either by formulation, so that you really weigh components and mix together and there you are, or by analysis. And the vast majority are certified by analysis. So material is prepared, and then expert labs take the samples and determine how much is inside. Your question is very relevant. Yes, this is a very important part of this.
Thank you.
All right, so now we come to the third way of classifying, which is most complex, or maybe the most difficult to understand. it is the meaning of the reference value. And there are typically two main possibilities. The reference value can be method independent, meaning whichever method you use, yeah, you get the right value, or it can be method dependent. Let me try to explain what it is. Let me also say that in some cases, also in names of documents and also in some slides, I have used myself the word procedure. But in this course, method and procedure are the same thing. So whenever I say method and procedure, you just know that they are synonyms. So if it is method independent, what that means? It means that we are determining some total content of something in something. For example, total lead in river sediment. This means the total mass of lead atoms relative to the sample mass. 56 micrograms per kilogram, for example. Okay. And what makes it independent is that you can use any total content determination method, meaning any digestion, any acid mixture, etc., as long as you know that it really fully digests the sample. Those of you who took atomic spectroscopy, you can remember how Vasily Rosen explained all those digestion things and so on. So you can, if one person used microwave digestion and the other one used just, like, let's say, boiling with some acid mixture, and both made sure that everything is digested, then their results are comparable. And of course, they are also comparable if one used ICP-MS, the other one used ICP-OES, the other used graphite furnace, atomic absorption, etc., etc. Okay, this is what people usually define, or sorry, usually determine. Most chemical analysis deals with total content. Yeah, if we take the same veterinary drugs, yeah, in meat, yeah, we usually even don't specify that it's total or not total. Obviously, it's all the veterinary drug that is in the meat. But it can be method dependent, and it can relate to only part of the analyte in the sample. So that instead of full boron content, we might be interested in bioavailable boron content soil. Interesting. Now, let me, again, I'm very ignorant. I'm not the soil chemist. Yeah, not at all. But still, agriculture people have told me that if you take total boron in soil, most of it is inside compounds that are completely inaccessible for plants, completely insoluble. Plants cannot get. And they tell that it's roughly 10 times different. Roughly 1/10 of boron in soil only is bioavailable. Meaning, if you digest everything, destroy all the soil, and you get nice boron content, which is good. And then for plants, most of it is not available. Boron maybe is not so well known example, but I think the best known example is phosphorus. Maybe some of you is to some extent familiar with agriculture and the agronomic things. Then a lot of phosphorus in soil is not accessible to plants. Like all that is what is in calcium phosphate, which is very hard to dissolve. But then hydrogen and dihydrogen phosphates, those are available. Okay. So that instead now of determining all the boron, you somehow have to leach or dissolve, etc., some of that boron out of that soil and then determine only that. The same thing goes about lead. Why is that, again, why is that here important? You see, quite some lead in nature is again in so insoluble material somewhere deep in the sediment. It's actually such a big concern. It simply sits there. It doesn't hurt anybody. Not fish, not microorganisms, not anyone. So rather, the problematic lead is what is soluble, or in this case, aqua regia extracted. Likewise, if you now think of from a position of a farmer, are you interested how much in total is phosphorus in your soil? Or are you more interested how much your plants can get? Most likely you are interested in the second thing, not in the first. And for this kind of analysis, people have to define a method. So what does it mean, bioavailable boron or bioavailable phosphorus? It means take the soil, you put it in a vessel, now you add some solution with well-known composition, some buffer solution. Now you fix the temperature very often. Now you mix well, you count how long you do this leaching. Okay. So it all needs to be specified how you extract that soluble phosphorus. Okay, now it's done. Now you filter. Now you get the liquid. And that liquid you now analyze. And the assumption is that, how much phosphorus went from soil into that liquid, that much also plants could in principle get. But if one person used one temperature, the other one used the other temperature, not comparable. If one person uses this buffer mixture, the other one uses the other buffer mixture, not comparable. If one person rotates like 30 minutes and the other one 6 hours, not comparable. Meaning, everybody has to use the same method. Differently from the previous case, that one used this acid mixture, the other one used the other acid mixture, all fine, because they all get the full total content. But here it's not that way. Please raise your hand who thinks that understood the logic. People on the internet? Everybody. Good. Yeah. And now I have here the question, why do we need CRMs with method-specific or method-dependent reference values? I actually answered this question already myself. The farmer is significantly more interested. How much phosphorus plants can get than just some abstract total quantity, which is not really so relevant at all. So here, essentially, we are only determining a part of the analyte in the sample, meaning the value is method specific. It's important to closely follow the method, and you can compare results between labs only if everybody used the same. Now, these leaching methods for this kind of analysis all are standardized. So there are ISO, ASTM, etc., all kinds of standards, so that people do those determinations always against some standards. They don't invent them themselves, because if they invent themselves, they cannot compare with anybody else. Well, they can invent if they want to do some fundamental scientific research. That's a different thing. But in routine lab, they don't invent. They need to follow standards. And here now is an example of a certified reference material. It's a certificate. Metals in river clay sediment. And it has both total metals, it also has extractable metals. And here, very important, is specified the extraction method. So this is the method, one ISO standard, how you extract with aqua regia. Please raise your hand who knows what aqua regia is. Please raise your hand who feels uncomfortable when I say aqua regia. Two persons. Okay. Aqua regia is a mixture of hydrochloric and nitric acid, concentrated hydrochloric, concentrated nitric acid, typically 3 volumes of concentrated hydrochloric and 1 volume of concentrated nitric. This is very powerful in dissolving different metals. It's called aqua regia, like king's water, if we did translate kuningvesi in Estonian. And it is king and regia is because it also is able to dissolve gold, which neither hydrochloric acid nor nitric acid individually cannot do. But these together, they dissolve gold. And yes, it's a very powerful mixture for dissolving. But some part of that of those metals in river clay sediment are not soluble in aqua regia, hot aqua regia. What that means? Not really likely. That river water at the typical temperatures that river water has at pH 7 or 8 point something will dissolve if hot aqua regia cannot dissolve. So that whatever is not soluble in hot aqua regia probably is not soluble. And now if you look, yeah, please.
I can ask a question instead then. I'm really curious how provided extractable metals via aqua regia are of any value when we are talking about river sediment and river water. Because still, if they are extractable by aqua regia, it is still really unlikely they will be extracted by water in any foreseeable future.
Again, sadly, I'm not educated enough to give you a good answer. I'm not an environmental chemist, but the trick, of course, is that in aqua regia you maybe do this extraction in 1 hour, but river has 50 years to extract. Yeah, so that probably I'm not saying that river is able to extract exactly the same amount of metals, but let's say they probably assume that whatever is not aqua regia extracted is completely safe. Whatever is might be problematic because among the metal content that is aqua regia extractable might also be part of metal which can be extracted with river water itself. The fact that something is aqua regia extracted doesn't say that nothing of this is river water extracted. So I think it probably is valuable. If they produce these CRMs, and LGC is a company who has to earn profit. I will later say something about production of CRMs also. If LGC finds it profitable enough to produce this CRM, then probably there are customers who find it very useful, that they are happy to pay money for that. Yeah.
Thank you.
Yeah. Okay. Now Christian has a question. I don't know MUs. There are MUs. MU is measurement uncertainty. Yeah. There are uncertainties. I simply did not put them here. Yeah. Maybe it even would be like educationally correct to put, but it's already so crowded slide. So I did not put the uncertainty. And now you can compare. Most cases not so big difference actually. Yeah. But in chromium, depending on which you take as the basis, the difference, if this is your basis, then this is more than 50% higher. So that there is some elements. But like copper, I did not even make the arrows. Copper is so similar, 96 and 92 milligrams per kilogram. Okay. Anybody, any question? Gleb?
Is it safe to assume that if the metal is not listed in the extractable metals, but is listed in total metals, then it is not extractable at all? There are quite a lot of those.
No, I think it rather is the other way around, that they are very well extractable. For example, sodium most likely is very extractable. Sodium is not chromium or lead that form all kinds of hydroxides and salts that are very poorly soluble. Almost any salt of sodium is soluble. So I think those here are simply not of concern. So sodium is not really any kind of a problem. I think it's rather the other way around. Yeah, that at least with sodium, there's probably no question. But of course, if we look at aluminum, aluminum is a tricky one. Yeah, that one can also form salts and oxides which are not soluble well at all. Why it's not here, I cannot tell you. With aluminum, indeed, I would say I would say not 100% of it is extractable, but some of it still should be extractable with aqua regia. I find it difficult to believe that nothing of aluminum is extractable with aqua regia. Doesn't look logical. I think it is they simply certify these elements like this and these elements like this. So this is like perhaps simply their choice how to certify. We have to file complaints to LGC. There's so many things that we don't understand. But of course, this was produced very long time ago. Yeah? Those people who did that back then might not even be working there. But LGC still has to be held accountable for this. Even, I mean, if some real problem is. Also, let me. Yeah, it seems that this will be our last slide today. Anyhow, let me add one more thing. This method, as you maybe noticed, to a large extent is the sample preparation, not so much the spectroscopic method. Because if you have already extracted and now you have a solution, now it's not really an issue whether it's ICP-MS, ICP-OES, or something else. And here also you can see that they actually use different techniques. Yeah, XRF, neutron activation, and they mention here chemical dissolution techniques. I don't exactly understand what this is. Dissolution technique is not like an analysis method, but this is what they. But yes, method first of all refers to sample preparation. So we stop here, but we still have time for questions. Any question, anybody? Claire, you seem to have a question.
It's not really relevant to the lecture. I was just wondering if extractable metals are the ones they listed are that may cause any harm or any environmental issues. And I was wondering whether zinc is considered cancerogenic to the environment or something. It's the first time I see it in such case where it is a concern to the environment.
Yeah, okay. First of all, indeed, your comment is very correct in the sense that extractable metals, yeah, with the exception of zinc, all are toxic, or let's put it elements, because selenium is not really a metal. And if we look up there, then all those elements except one, all the elements up there for which there are, except one, yeah, for which there are no extractable element content are not really toxic. So aluminum, calcium, copper also not so. Yeah, copper, by the way, is down. Barium is the exception. So barium is a toxic element. But I think barium, it might also be that maybe it is like dissolvable sufficiently well without aqua regia. Maybe, I don't know. Why zinc might be down there? Yes, zinc is not really any kind of highly toxic element, but of course, if you look, the concentration is quite big. It's 0.5 gram per kilogram. This is a lot. Of course, barium also very big.
I also looked at the concentration of barium was higher than the zinc and
yeah.
Victorian.
Apparently, this is simply a river sediment which has concentrated in it a lot of those elements. I did not specifically check, but some of those reference materials, again, are like natural levels, but some are specifically for contaminated situations. So this might be from some contaminated area.
Can I ask one last question?
Yes, even several if you wish.
So is it usual that providers of certified reference materials don't explicitly tell you what this reference material is for? Like in this case, it's not obvious how I should use the information of total metals and extractable metals, but rather the customers are the ones that decide what reference materials they want and how they will be utilizing them. Okay. Is it common they have no guide for you to how you should use this reference material or reference method?
You are tempting me into opening another file. Okay, but I think I will not do that because you might want to go to cafeteria. You see, what you see here in front of you is a tiny piece of the certificate of that reference material. Later on in this course, by the way, it's already in Moodle. You can open it. We will look at one certificate, sample certificate, to see what information is there, and one certification report. The certificate has a lot of more information than here. Usually the certificate does give some indication about what it should be used for, but of course, actually, it is more for the customer to determine how he or she wants to use it. So it's not so much for the certified reference material producer to tell that, but they usually put in some sentences that, yes, it's meant for this, and this. Maybe next time, maybe the time after the next time, we will look at that example certificate. I will then explain you some things that you find there, and you can then get the idea that it's actually much more information rich than this one slide. Yes, Christian asked, where are the uncertainties? I simply did not put here. Yeah.
Thank you.
All right. Any other questions, anybody? Apparently not. So thank you. And don't forget then to start discussion about the test. Yeah.